Hello, students. Welcome to your Chapter 5 review video. I just want to take a little bit of time and show you the types of things that I might ask you to do on a Chapter 5 test, which is coming up at the end of this week. Or if you're watching this on Thursday, then it's tomorrow. So we're going to go through these key ideas. I sent you this document as well. And I crossed off a couple of them, as you can see here. So we just have these six things to worry about. We're going to go through 4 problems, which should cover pretty much everything in terms of what I need you to do. The first thing that's listed there is transforming rational functions, which basically means making graphs or writing equations that look like this. Okay, and these are things that hopefully at this point we should recognize this kind of thing as, you know, our double whooped graphs that's been shifted over and shifted up in this case. So if I just go real quick through this, sketching this graph here, the horizontal and vertical asymptotes, originally, remember, when we just had the equation 1 over x, we just had that equation, our horizontal and vertical asymptotes were both at 0, but this function has been shifted to the right by 4 and up by 1. So it makes my asymptotes do the same shift. Okay, so we shift the asymptote up by 1, and we shift it over by 4. We'll say that's about there. Okay, and those are my new asymptotes. And their intersection point, remember, is what I now think of as the origin. Okay, it's not actually the origin on the graph. It's actually the point 4, 1, 4 in the x and 1 in the y. But that's what I use as my origin to find my coordinate points. And remember, I find the coordinate points by finding numbers that can multiply to be the top of this fraction. In this case, it's a positive 1. So my only choice is 1 and 1. So I go 1 in each direction from my intersection point of the asymptotes, over 1 and up 1, and then also this way, over 1 and down 1, which actually ends up down here on the x-axis. And then remember, these asymptotes I get very, very close to, but I do not get to cross. And my graph looks something like this. Okay, so that would be a sketch of this graph. Now, the equation for these asymptotes, the vertical asymptote here is at x equals 4. Okay, that's one of my asymptotes. And then the other is at y equals 1. So you may also be asked to take a couple, like you're given the equations of the 2 asymptotes and you're asked to write the function. So just remember that when your vertical asymptote is now at x equals 4, it's been shifted to the right by 4, which maybe is backwards for you guys. It's shifted to the right by 4. So that shows up as a minus 4 on the bottom of the fraction with the x. And then the y being 1 means that that's been shifted up. Okay, that's been shifted up by 1, so that's why we see the plus 1 at the end. So that's the deal with transforming rational functions. You might be asked to make a graph. You might be asked to write a function. And yeah, that's how those 2 things are related. The other thing that we did in terms of making graphs ourselves was we could be given a graph, for example, something that looks like this, and we might be asked to graph 1 over that function. So this is what we call the reciprocal graph, remember, because we flip it over and we put 1 over the function. Remember what that does here. It turns all of our x-intercepts, into vertical asymptotes. Okay, so that's the first thing that this does. Takes my x-intercepts, turns them into vertical asymptotes, which means I have a vertical asymptote here, I have a vertical asymptote here, and I have one way over here. Okay, so I have 3 vertical asymptotes when I flip this particular function over. And once I have those vertical asymptotes, I can get a pretty good idea of what the function looks like. because if we take, for example, this section here in between these two vertical asymptotes, I have on either side the function, the original function, getting smaller, right? It's getting closer and closer to 0. So if my function originally is getting smaller, getting tiny, what happens to the reciprocal function? Well, it gets very, very large. So I know that as my function goes towards 0 at this x-intercept, my reciprocal function is going to be going up towards this vertical asymptote, and of course never cross that vertical asymptote, but get very, very close to it. Okay, and the same thing happens on this side. It goes up towards that vertical asymptote like that. And then this is the top, like the peak of my function in this section. So it's up at what, 1, 2, 3, 4, 5. So if I put 5 here as my function's value, when I flip it over, that becomes 1/5. So it gets very, very close to 0. Right? And generally, my function is going to get very close to 0. So from this point, then, it's just going to curve up, and this section is going to look basically like a parabola. I can't guarantee that it actually is an x-squared graph, but that's what this piece is going to look like. Okay, it takes this arc, and it sort of flips it over and extends it up forever. Now, this piece here is going to do something similar, right? Here it's getting close to 0, and so it's going to go the other way like this. Here it's getting close to 0, and so it's going to go up the other way similarly. It's just going a little bit slower. And then in the middle here, this is my peak, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1/9, like right about there. And so this side goes very quickly. This side goes a little more slowly, okay? So this also sort of flips this piece over of my original function, takes that and flips it over so that it's going upside down. Just basically remember, as my original function is getting further from 0, my flipped over function is getting closer, and the opposite is true as well. Okay, and then outside of these asymptotes here, like working on this left side, here I see again my function as I come up is getting close to 0. So I know that that is going to go the other way along the vertical asymptote. And then I just see it getting very, very far away from 0. You see that arrow points down forever. So that's getting really, really big in the negative. And remember, when things get really big in the negative, they get very small when I go to the reciprocal function. So that becomes like that, a horizontal asymptote at 0. And something similar here. On this far right side, I'm in the positive now. And so here I'm getting closer to 0 in the positive. So it's going to go up along that vertical asymptote. And then it's just going to keep going up and up and up and up and up and up and up forever. And so my function, when I reciprocate it, when I go to the reciprocal version, it's just going to come down along the 0 and do that. Okay? So when you're asked to sketch a graph of 1/f of x, remember these things, that flipping the function over turns the x-intercepts, wherever it crossed the x-axis, into vertical asymptotes. And it turns, or I should say, when original function is approaching 0, reciprocal function is going to infinity, or possibly negative infinity, right? And then the opposite is true as well. When the original function is going to 0, the reciprocal function is going to infinity. When the original is approaching infinity, the reciprocal approaches 0. Right, so that should help us get a pretty good sketch then of any reciprocal function. Given a graph, we can graph its reciprocal function. All right. Next on the list was the definition of a limit and one-sided limits. Okay, and that's the rest of this chapter is basically about limits of functions from equations or from graphs or piecewise functions, etc. So if we're given this function and we're asked to find these following limits, let's just start with this one over here and review what this notation means. This is saying x approaches 4 from below, right? From the negative, from less than 4. So what we would do in general is we would look at the graph of this function, put our X or put our cursor or put our pencil a little bit lower than 4, and then approach 4 from that direction and see what our function does. All right, so I'm going to go ahead and do that here actually. I'm going to get rid of that, and I'm just going to punch in this function right here, f of x, remembering to put parentheses, 3x plus 2 in parentheses divided by, in parentheses, x minus 4. Okay, so I'm going to do this. Now I'm going to hit my window and make sure that I adjust the x min and max to be right around the limit they're asking me to find, right? What do they want me to approach? They want me to approach 4. So I might go maybe from 0 to 8, go 4 on either side of that value they're trying to get me to find. And my y values, I might just go back to normal, -10 to 10, and see what it looks like. I can always adjust it later if I need to. So if I click graph, I think, okay, all right, generally I can see, let's see, 4 is going to be, let's see, I can make the screen bigger now for you guys. Maybe I can. There we go. Okay, so x equals 4 is going to be here. 1, 2, 3, 4. So it's going to be right here. And remember, I'm approaching 4 from below. So I'm going to go back here to maybe 2. I'm going to go to my function, and I'm going to go towards 4, and I'm going to see what is my function doing as I go towards 4. As I go towards 4, it's basically going down forever. It's never going to stop, right? 4 is a vertical asymptote for this graph. And this function, like I can show you if I made my y min, for example, -50, and my y max 50, you can see even more of what's happening here, right? There we go, okay? So this is x equals 4. If I start back here at 2 and I work towards x equals 4, I'm going to go down forever, which means the limit as I approach 4 from the negative side is going to be -infinity, okay? Because I'm going to have no bound on how low I can get. -infinity, okay? Now the next thing is actually asking me not for a one-sided limit, okay? So not from below or from above, but from both sides, okay? A two-sided limit. And remember, in order to have a two-sided limit, we have to have both sides from below and from above agree with each other. Okay, they have to agree. So they have to think they're going to the same spot. Remember when we first did this, we put little bugs on our function and we made them walk, and we asked where do they think they're going to end up? They need to think they're going to end up in the same spot. So if I go back here and I go to 4, because that's what it was asking me about 4. Well, before I do that, what should be my first thing I try when I'm asked to find a two-sided limit? I should just try plugging it in, right? Now, based on the graph, we sort of already know that that's not going to work in this case, but we can go ahead and try plugging it in if we want to. Anytime you're given a two-sided limit, or asked to find a two-sided limit, you can always plug it in and see what you get. So if I plug 4 into this function, the top of the fraction, 3 times 4 is 12, plus 2 makes 14. And then on the bottom, 4 minus 4 is 0. Okay, so I get 14 over 0. And that's where we run into our problems, right? 14 over 0 is not allowed to happen. So when we get something undefined, when we plug in a value, we have to go to the graph. So that's why we went here. And now we can see sort of why it's undefined, right? On both sides of x equals 4, coming from one direction, I think I'm going to -infinity. Coming from the other, I think I'm going to +infinity, right? Do those sides agree with each other? Do they think they're going the same place? No, they don't. So what do we say about the two-sided limit as x approaches 4? We say it does not exist, or DNE, does not exist on both sides because they don't agree with each other, all right? The last one here, they're asking me to find the limit of this function as x approaches 6. It's a two-sided limit that I'm asked to find. So first thing I'm going to try when I'm asked to find a two-sided limit again is just plug it in. So let's see what we get if we plug 6 into this function. Let's see, the top of the fraction, 3 times 6 is 18. 18 plus 2 is 20. So I get 20 over 6 minus 4 is 2. Does this work out okay? Sure, 20 divided by 2. As a fraction, you can leave 20 over 2, but of course we would want to reduce it. It reduces down to 10. 20 divided by 2 is 10. So the limit as x approaches 6 from both sides is 10. Remember, that trick works when you have a non-piecewise function, or you're at least not at the boundary point. So that we're talking about 4, 5, 6. We're talking about this point right here. So yeah, it looks like as I come from this side and as I come from this side, they're going to agree on that point right there. Okay, that's y value of 10, function value of 10. So one-sided versus two-sided limits, we have some different strategies. One-sided, we're almost always going to look at the graph. Two-sided, you can try plugging it in. If that doesn't work, you can look at the graph. All right. Okay, the last piece, and possibly the most complicated, is piecewise functions and limits of piecewise functions. And not only that, but within that, we sort of look at what does it mean for a function, specifically a piecewise function, to be continuous. All right, so in this case, this is the function that I'm given. Whoopsies, that's not what I meant to do. This is the function that I'm given. Okay, and I'm going to ask myself a couple questions. Number one, is it continuous at x equals 3? In order to answer that continuous question, I'm going to actually answer all these limit questions over here. Okay, so the first thing that I'm going to try to find is what is the limit of this function as x approaches 3 from above. So from more than 3, from higher than 3. That's what the little plus sign tells me. So what I should realize is when I look from above at this function, I'm looking at this piece right here. Because this says for x bigger than 3, right? So when x is bigger than 3, I'm going to be using this piece of my function rule to get all of my points. So as I approach 3 from above, I'm going to be following this graph, 3x squared. So if I just quick give myself a little sketch here. As I approach x equals 3, which is going to be somewhere out there, I'm going to be following 3x squared, which is going to be like a parabola, right? So it's going to be, doing something like this. And then on this side, obviously, I wouldn't have it because I don't get that part of the graph. And this would actually come all the way down to here. So I have this function. Okay, and this is my 3x squared for x bigger than 3. The reason I'm using x bigger than 3 is because it says 3 plus, right? From the positive, from bigger than 3. So if I want to know the limit as I approach from this side, with a piecewise function, if I'm approaching the boundary point, I can just plug this function, or excuse me, this value for x into that piece of my function rule. So as I approach 3, I think I'm going to get to, well, let's see, 3 times 3 squared. 3 squared is 9. 3 times 9, I think, equals 27. So as I approach 3 from the positive, I think that I'm going to get to a y value of 27. So that's what this limit is equal to. The limit as x approaches 3 from the positive is equal to 27. And that came from using the bigger piece of my function, because I'm bigger than 3, and just plugging that value, that boundary point value in. So I think I'm going to get to 27. Now, in this particular case, am I actually going to get to 27? No, I'm not, because this is an open circle, right? Because this is not equal to, it's a not equal to piece. So I don't actually get there, but that's where I think I'm going to get if I use this bigger piece for bigger than 3, bigger than 3. If I go to this other one, the limit as x approaches 3 from below, from the lower side, from less than 3, from the negative, I'm going to be using this piece of my function, right? When x is less than or equal to 3, because I'm approaching from numbers that are less than 3. Again, that's what the minus means. So if I plug 3 into this piece, that's going to tell me the limit from the lower side. Obviously, this one told me limit from the upper side. So if I plug 3 in here, 8 times 3 is 24. Negative 3 plus 24, that I believe gets me 21. 21. Okay, so that would be somewhere like lower than this point. I would have a point somewhere lower than that here, and then it would be something like this, right? That would be a straight line, but you get the idea. That's what my function would look like. So what we should notice here is my next limit question is, what is the two-sided limit? What is the two-sided limit as x approaches 3? Well, let's think about the two-sided limit from both sides, from the positive, from the negative. Do they agree? And if so, what value do they agree upon? Well, unfortunately, in this case, they don't agree. So I'm going to say does not exist, right? Because this two-sided limit doesn't exist. Because my two sides, my left, my positive, my negative, my left and right side don't agree on a limit value. They don't agree on a function value. One thinks it's going to be 27, the other thinks 21. So it doesn't exist, all right? Now, I'm going to pause here, and I'm going to look at then this question about x equals 3, and I'll come back to this last limit question and tell you one more thing about piecewise functions. So the other question I'm asked is g of x continuous at x equals 3? And one thing that we should remember are the 3 criteria for a continuous function. Number 1, the function has a value, right? Number 2, the function has a two-sided limit. And then number 3, the value, I should say the function value and the two-sided limit, they need to agree, right? So these 3 things, if we can check all 3 of those boxes, then we have a continuous function. Can we check all 3 of those boxes for x equals 3 in this case? No, we can't. And the most obvious one that we can't check off is this one. The function has a two-sided limit. What did we just say about the two-sided limit as x approaches 3? It does not exist. Therefore, it doesn't have a two-sided limit, so it can't possibly be continuous. So in this case, is g of x continuous? No. G of x is not continuous at x equals 3 because it fails that second criteria, okay? So that's how continuous is sort of connected to the idea of limits, right? Okay, and then the last question for us is, what is the limit of this function as x approaches 4? Now, the first thing I want you to recognize is when you're asked to find a two-sided limit for a piecewise function, the first thing to decide is the limit value they're asking for the boundary point where I go from one piece of my function to another. In this particular case, no, they're asking about x equals 4, and my boundary point was x equals 3. So when you have a two-sided limit for a piecewise function that's not at the boundary point, then we can simply do the two-sided limit like we did before. We can just try plugging that value in. If we get something undefined, we'll have to look at the graph, okay? But in this case, if I plug x equals 4 into the function, the first question is, which piece of the function should I be using? Should I be using this piece or should I be using this piece? Well, 4, last I checked, was bigger than 3. So because 4 is bigger than 3, I need to be using this piece of my function right here, not that one up there, because that was for x less than 3. This is for x bigger than 3, which 4 certainly is. So what I'm going to do is I'm going to plug 4 into this function here, that part of my function rule. And it's going to say 3 times, in parentheses, 4 squared. What is 4 squared? 4 squared is 16. 16 multiplied by 3 is 48. So the value of the function, and the value of the limit, the two-sided limit, as x approaches 4, is 48. Okay, because I plugged in the value because it wasn't my boundary point, and I got a perfectly fine y value. So when you are given or asked to find a two-sided limit of a piecewise function, if it's not the boundary point x value, you can just do your two-sided limit like you've been doing all the rest, plugging the value in unless it's undefined, in which case you look at the graph, okay? So that's sort of just a real quick overview of everything that we dealt with in Chapter 5 in terms of limits, some extra special rules about limits, when we can use certain shortcuts for limits, What does it mean for something to be continuous? And then, of course, going back to graphing reciprocal functions and transforming our rational functions, okay? If you have any questions about any of these key ideas, please reach out to me before you take your test. Otherwise, that is all I have for you, and we'll talk to you soon.